How does the first law relate to coefficient of performance? Have you ever wondered how energy is managed in systems like refrigerators and heat pumps? Today, we will uncover the connection between the first law of thermodynamics and the coefficient of performance. The first law states that energy cannot be created or destroyed. Instead, it can only change forms. This principle is crucial in understanding how thermodynamic systems operate. In simple terms, the first law tells us that the total energy entering a system equals the energy leaving it plus any change in internal energy. For refrigerators and heat pumps, this means that the work done plus the heat taken from the cold space equals the heat delivered to the hot space. We can express this mathematically as heat delivered to the hot space equals heat extracted from the cold space plus work input. Now, let's talk about the coefficient of performance, often referred to as COP. This is a measure of how effectively a refrigerator or heat pump uses work to transfer heat. For a refrigerator, the coefficient of performance is the heat removed from the cold space divided by the work input. For a heat pump, it is the heat delivered to the warm space divided by the work input. The first law directly influences the coefficient of performance by establishing the energy balance that determines how much heat can be moved for a given work input. Since the heat delivered to the hot space equals the heat extracted from the cold space plus the work input, we can see how the coefficient of performance is calculated. For a heat pump, we can also express the coefficient of performance in terms of the refrigerator's coefficient of performance. This shows a direct relationship between the two. Higher coefficient of performance values indicate that more heat is moved for each unit of work, which means better performance. The first law also sets limits on the coefficient of performance. For instance, the Carnot cycle, which is an idealized cycle, defines the maximum possible coefficient of performance based on the temperatures of the hot and cold spaces. The formulas for the Carnot coefficient of performance for heating and cooling depend on these absolute temperatures. In essence, the first law of thermodynamics provides the foundation for understanding the coefficient of performance in refrigerators and heat pumps. It explains how work input and heat transfers relate, allowing us to measure the effectiveness of these devices in transferring heat relative to the energy they consume. Understanding this relationship helps us appreciate the efficiency of thermodynamic systems and cycles.